Hey, I'm going to go through AP Physics C differential equations. Just a rough idea of what you might find when you get into an AP Physics C problem, free response. And let's just talk about, I don't know, air resistance, okay? So we have mg, and let's just say a ball is falling with a resistance against the motion of kv, okay? kv. So what's going to happen is, again, when we talk about air resistance, once we drop something from a high point, let's just say this is where we're dropping it from and this is where it's going to, as it falls, at the beginning it has no velocity, so the acceleration is mg. Then as it falls, it gains velocity, so then there's mg this way and kv this way. So the acceleration is less and less and less. I drew this a little wrong. I should draw this with kv a little smaller than mg. Because most of the time, as it's falling, that will happen. Finally, it gets to a certain point where it's going fast enough that kv is equal to mg, and that's terminal velocity. So just setting an expectation, we should see the velocity increase and asymptotically approach a certain value. So we should be looking for something that looks like this, if we're talking the positive direction. And this is going to be the terminal velocity where kv is equal to mg. So let me just write that. Terminal velocity, we know, let's call this down positive. mg minus kv equals 0. That's our Newton's second law. And so terminal is when it will not go any faster. mg equals kv, and we solve that v is equal to mg over k. That's our terminal velocity. So that's going to be what that asymptotically approaches, mg over k. Now let's derive it, because it's very important to understand the concepts and to predict what that graph is going to look like, but it's also important to get all the points you can, and to get all the points you can, we're going to have to do a little differential equation here. So what they're generally going to say is something like write a fundamental, write an equation that you could solve, but do not solve, you could solve to find v as a function of time. Excuse me. And it should be based on a fundamental formula. And so generally when we're talking about motion, we're talking about the fundamental formula being sum of forces equals ma. So we just write our Newton's second law. Anytime you can draw a free body diagram, you're probably going to be using Newton's second law. So we'll have mg minus kv equals ma. Now, what's really important is to understand that the acceleration and the velocity are related. Okay, this is what we're talking about when we're talking about a differential equation. Sometimes in electricity, we might have Q and I. And so I is dq dt. Well, A is dv dt. So we're going to write this now. This would be the differential equation, m dv dt. So that would be what they'll generally ask for first. They just want you to write the equation based on a fundamental formula that allows you to solve for v. And they'll say, but don't solve. Then the next step, they'll say, okay, now solve. Now what's crazy is this would get a point. This would probably get a point. I'm not even 100% sure. This next part, I think, is also only 1 point. I'm not sure. But what we want to do is we want to separate the v and the t. And it looks like it's going to be this hard thing. Let's add a kv to both sides. No. The easy way is just try to get that dt alone. So you end up, let's multiply both sides by dt and divide both sides by mg minus kv. And you end up with m dv over mg minus kv. Okay, so this you can see is a constant times a function of v there with the dv on top. That's going to end up integrating to a natural log. I'm not going to worry about this absolute value or anything like that. I'm just going to try to go pretty quick on this. I'm already going pretty slowly. So integral of this, let's integrate both sides. And the integral of dt is going to be t plus a constant. And this, we could say u equals mg minus kv. So we're doing integration by substitution. du is negative k dv. So we've got the dv. dv equals du over k. I should say negative du over k. So I'm going to substitute this in for dv, and we have m over k. I'm just going to put that there. Negative du over du. Okay, so we have 2 plus c. When we do the integral of this, of negative du over, that's supposed to be a u, sorry. Then we end up with negative m over k, log of du, log of u, and u was mg minus kv. And I'm going pretty quickly over that, I understand. That's a calculus thing. Bottom line is you are integrating this however you can do it. And we're going to end up with a c on one side or the other. Now, what we're going to tend to do is we're going to tend to get rid of that log by doing e to the whatever. So we want to divide by negative m over k. That brings over here negative k over m times t plus c. And yeah, we did divide c by this constant, but that's just another constant. You could call that c1 and call that c2, but it doesn't matter really. It's just a constant there. Now to get rid of the natural log, we're going to do e to the both sides, e to the, and this ends up just being mg minus kv on this side, and e to the negative kt over m plus c. Well, if we think of this, I'm not going to do this in 2 steps. This is the same as e to the negative kt over m times e to the c. Well, e to the c is just a constant. So I just generally rewrite this as c times e to the negative kt over m, a different constant. Okay, so I'm getting a lot of different constants. So make sure you can do that very quickly. You don't want to be thinking about that too much. Equals mg minus kv. Okay, so we're getting there. We're almost there. Now what we want to do is we want to solve for that constant. So generally there's an initial condition, and the initial condition in this case, if I dropped it, let's just say v0 equals 0. So at t equals 0, we know the velocity is 0. First of all, let me rewrite. I'm being lazy here. Let me rewrite this. If I rearrange this whole thing, I get v equals mg minus c e to the negative kt over m. I just did algebra to get that over there, all divided by k. All divided by k. And again, that's c. It's just c over k now. It's another c. That's probably my 4th c. Okay, so but it's still a constant. So now I have this, and now what I want to do is I want to evaluate it at t equals 0. At t equals 0, that velocity is going to end up being 0. So mg over k minus c times e to the 0, which is 1. So we end up having this. So the constant equals mg over k. So now I'm going to have my final form for this is going to be v equals mg over k minus mg over k, just plugging that in for my constant, times e to the negative kt over m. That ends up being mg over k times 1 minus e to the negative kt over m. Okay, so let's see how that plays out. When time is infinity, so way, way, way off there, e to the negative infinity is 0. So this just ends up being mg over k. Let's go back here. And that's what we calculated for our terminal velocity. And so if we graph that, it's going to end up looking like this. This is a classic 1 minus e to the negative something times t. Okay, if you have e to the negative something t, it's a declining, it would look like this. Okay,